Now, the big question now is, okay, so that's cool that we can go and take the, calculate the specific heat of something in a calorimeter, but ultimately what we're interested in is chemical reactions. So how do we work with chemical reactions? So we're going to study today two types of calorimetry that we can do with chemical reactions. And on Wednesday, we're going to wrap it up by telling you some of the manipulations that we can do with the data that we obtain from calorimetry. So let's start out by considering a process at constant volume. Process at constant volume, okay? Remember we said the formula, the change in energy for a system, in this case a chemical reaction, is Q plus W, heat plus work. And we said that the work is essentially minus the pressure times the change in volume, representing the expansion or compression of a gas. Now, let's say that I do an experiment where I keep the volume constant. And there's a name for this. This is called an isochoric process. Isochoric process. Let's do the math on that equation up there, all right? Remember, if the volume is constant, that means delta V is 0. And therefore, the only energy exchange that you have is heat. And we put a subscript V in there. Have you noticed that, right? This little subscript here, V, just to represent that this is the change in energy for a process at constant volume. In other words, an isochoric process, all right? So let me tell you what kind of apparatus we're going to use for this. It's very interesting. Okay, wait for it, wait for it. It's called a bomb calorimeter. That's right. It's a bomb calorimeter. So this is essentially, again, it's kind of like a system that consists of two tanks, all right? There is an interior tank, and that's our system. And essentially what you have in it is you have oxygen, and then you have an electrical source to give you a spark. And you're going to have essentially material in here that is combustible substance. In other words, this is a apparatus that's designed to measure combustion reactions, okay? Reactions that are very exothermic. And that interior part is what we call the steel bomb or the bomb. That's our system. Now, surrounding that is an enclosed tank or jacket that has water in it. So once more, in this case, water becomes part of the surroundings. Notice that again, we have a stir and we have a thermometer. So we are measuring the change in temperature of the water. However, in this particular system, we're going to have to be careful to account for the actual exchange of energy with the calorimeter itself. In other words, the metal inside the insulated jacket. All right. Before we do that, let me tell you a little bit of history here. Around 1890, scientist named Wilbur Atwater had the idea of putting food in a calorimeter, burning it, and measuring the amount of heat produced. And he found that different types of foods produce different amounts of energy, right? So what he did was, back in the day, before scientists understood that heat and work were both forms of energy, and believe me, here, let me tell you this side story before I go on. I don't know, I got to tell you this. In the old days, like in the 1800s, there was a theory that heat was some kind of a substance. In other words, it was called a caloric. And the idea was that this substance was exchanged between the system and surroundings. And so because of that, scientists had these ideas of the calories and that kind of stuff, until later on, they figured out that heat and work were actually two forms of interchangeable energy. So anyway, back to the story here. So essentially, this is the origin of how, the food calorie counts started. So he basically designed the foods according to their caloric content as ways of measuring the efficiency of diets, okay? So a little bit of history for you guys in there. Okay, let's go back to our bomb. Remember, the reaction that happens in the calorimeter is going to be a exothermic reaction, right? Don't forget, exothermic. Heat is going to be released by my reaction into the tank. The water in the calorimeter absorbs the heat, and of course, its temperature increases. So let's see if I can get this thing here to go. Don't worry, I'll come back to this. So once more, there's a heat transaction for the reaction and a heat transaction for the calorimeter. And once more, according to the law of conservation of energy, there should be no net change of energy because the calorimeter is isolated from the outside. All right, let's go back here. So what's going to happen, therefore, is just like before, because the total energy change was 0, I can use that equation there on the top right. And like we did before, we can say that the heat of the reaction is minus the heat exchange for the calorimeter. And the formula for calculating the heat exchange in the calorimeter is C times delta T. So instead of MCAT, this is just CAT. C of the calorimeter represents the heat capacity. What we've done is we have to pre-calibrate the calorimeter and figure out in that calorimeter, and that includes the water in it, but also includes, of course, the steel container of the bomb and also the interior of the insulation jacket of the calorimeter. So all of those components form our surroundings, and so we had to calibrate it to find the heat capacity of the calorimeter. All right, so that's kind of like the way it works. Okay, let's do this. Let's do an exercise here, and I hope this is in your notes. So we have this question here. Oops, let's see if I can find my... One second. I'm gonna find my paper here. Here we go. Sorry. All right. 5.00 grams of methanol, which by the way is also called wood alcohol, is burned in a calorimeter. The temperature of the calorimeter increases from 20.0 to 35.0 degrees. The heat capacity of the calorimeter is 7.70 kilojoules per degree Celsius. What is the heat of combustion per gram of methanol? All right. So again, first thing I'm going to do is, well, what is the heat change that happened in our sample? Don't forget, whatever happened in our sample here, all right, whatever exchange was exchanged, and we're going to say this is our sample here, plus whatever exchange happened in the calorimeter should add up to 0. So that means that the exchange of energy for my sample was the negative of the exchange of energy for our calorimeter. And that's where we use that CAT formula, right? So this would be C of the calorimeter times the temperature change in the calorimeter. Okay, so that would be, they tell us here the heat capacity is 7.70 kilojoules per degree Celsius. Notice that this is not the specific heat. In other words, this is not per gram. This is for this calorimeter. So the units are just simply kilojoules per degree Celsius. The temperature change, final minus initial. Final temperature was 35.0. Initial temperature was 20.0 degrees Celsius. All right, so let's see what that is. 35 minus 20 equals 15, but remember I had a decimal there, so this is really 15.0. So that's 3 sig figs. And now I multiply times the heat capacity. and I get 115.5 kilojoules. All right. Now, here's what I can do. I can either round it up at this point, or I can say, well, let me save it in here and I'll round at the next step, okay? So technically this would be 111, 115.5. Oh, by the way, I forgot to do something and nobody told me. This is a negative here, right? Negative there, negative there, all right? And this would be kilojoules. Now, the thing is, the question asks, what is the heat of combustion per gram? So this is the heat of my sample, but I want to find out, according to the question, what is the heat of the sample per gram? So that would be minus 115.5 kilojoules. But don't forget that that was supposed to have been rounded to 3/60, right? I just don't want to start all over again. I want to leave it in my computer there. And we said we had 5.00 grams. So I'm going to take the number I had here, put a negative on it, divide by 5.00, and that gives me 23, negative 23.1 kilojoules per gram. Okay, so there you go. Hopefully you were able to follow along. And if you have any last minute questions, let me know. Again, okay, so here's another practice exercise. It says compound A is burned in a bomb calorimeter that contains 2.50 liters of water at 21.0 degrees. And I know you're asking right now, hey, Dr. D.A, where is that? So I'm gonna let you guys a chance to write it. I'm gonna put it here on our doc cam so you guys can write it down. I don't think that this actually made it into our into our PowerPoint set. So let me take you guys there, over here, and there we go. So here's the question. Let me see if I can zoom this in a little bit. There, so better. Okay, let me give you a chance to write it down because again, like I said, I may have forgotten to totally put this in your PowerPoint set. So compound A is burned in a bomb calorimeter. That's the one we just discussed. That contains 2.50 liters of water at 21.0 degrees Celsius. If the combustion of 0.175 moles of this compound causes the temperature of the water to rise to 66.0 degrees, what is the molar heat of combustion of compound A if the heat capacity of the calorimeter is 10.47 kilojoules per mole? All right. Again, notice this is the molar heat of combustion. All right. And they give us the heat capacity of the calorimeter. All right. Okay, so remember again, as we said before, whatever heat was transacted by our reaction is going to be the negative of whatever heat was transacted by our calorimeter. All right. So let's see what would be the heat transacted by our reaction. Be minus the heat capacity of the calorimeter times delta T of the calorimeter. Let's see what that is. Minus heat capacity calorimeter is 10.47 kilojoules per degree Celsius. And it says the temperature change here was the water started at 21 and it ended at 66.0. I mean 21.0 to 66.0. So that's going to be our temperature change that we consider in this case. So 66 minus 21.0 degrees. We'll discuss the nuances of this kind of stuff, but realize that the assumption is that when we start at 21 degrees, it says the temperature of the water because that's where the thermometer is. But we assume that the whole calorimeter is at that temperature. Similarly, when it reaches 66.0 degrees, the assumption is that although what we're reading is the temperature of the water, the whole calorimeter is increasing temperature to 66.0 degrees. All right? So if we do this calculation, all right, we're going to get 66.0. Of course, my calculator is not going to respect that 0.0 there, I think. Minus 21.0. It'll be 45. That's 2 sig figs. Actually, 3 sig figs because remember that we had decimals in here. Just my calculator doesn't respect that at all. Times 10.47 kilojoules per degree Celsius. And there's a negative in there. So to 3 sig figs, this is going to be minus 471 kilojoules. Okay, so we know how to do this already. However, there's something interesting about the question. It asks for the molar heat of combustion. And what that means is how many kilojoules per mole are released by this reaction of compound A. So the molar heat of combustion would be whatever the reaction transacted here divided by the number of moles of substance we had in there. So we have minus 471 kilojoules divided by the number of moles, which is 0.175. And let's bring our calculator again. I already had that number in there. And I'm just going to go ahead and divide by 0.175. And that gives me a total of minus 2,692 point bunch of digits. But my two numbers here only carry 3 sig figs. So I need to round that up to about 2,690, I guess, minus 2,690 kilojoules per mole. Okay, so I think the key thing here is to always make sure you read the questions and understand what they're asking for. Are they asking for how much heat was exchanged? Are they asking for how much heat per gram is produced? Are they asking for the energy per mole? So make sure you read the questions carefully, okay? So you don't get a wrong answer just because you didn't read the question correctly. Okay, let me come back here to our PowerPoint again. And again, sorry that I forgot to put that in your data set, but trust me, you can write it down. And like I said, I will upload a scan of these different pages that we're writing on. So now we know that we can express the heat of a combustion reaction either in kilojoules per mole or kilojoules per gram. Let me show you this interesting table here. If I can get this thing to work. Oh, there we go. So this is a table that shows us on the left different kinds of fuels. Has a name, and then in the second column it has the formula in case you're interested. And then it gives you the heat change. Now look at the top. This is the typical reaction for a combustion reaction. We studied these in Unit 4 when we studied chemical reactions. A substance reacts with oxygen in some kind of stoichiometric fashion to produce carbon dioxide and water. If you look here, it shows you what are the different amounts of energy released per mole and per gram. Let's look at the heat per mole because we just calculated that. You'll notice at some interesting things here. For example, let's consider methane. That is the gas that we use in the lab for our Bunsen burners, or you use in your kitchen for your stove if you're getting it from the company. So negative 891 kilojoules per mole. That's how much energy is produced per mole of methane. Now, in your cars, most of us use gasoline, and the fuel in there is called octane. And as you can see, it releases roughly several times more at 5,471 kilojoules per mole. So you can see that on a per mole basis, it looks like octane releases more energy. But think about it, that makes sense. If your reaction essentially consists of breaking down your substance, and you can see that most of these substances contain carbon in them, and each carbon is going to end up as carbon dioxide. Well, the more carbons you have, obviously, the more carbon dioxide generate, which means the amount of energy per starting unit is going to be much larger. What's interesting is that from our perspective, the question I ask is rather, well, how much of that fuel do I need in my tank to last me, as long as I need it to last? And as you can see, when you calculate the kilojoules per gram, it's interesting that technically methane gives you a few more kilojoules per gram than octane. In other words, it's kind of like a lighter gas. And of course, if we could carry in our tank, we don't want to do that. But if we could, we would love to do that. Now, I want you to look for a moment at hydrogen at the very top. And look at the amount of energy you get per gram of hydrogen. It's almost like 3 times per gram what you get with octane. In other words, if hydrogen were like a fuel, like gasoline, you would only need 1/3 of the weight of hydrogen in your tank to give you the same amount of energy that a full tank of octane or gasoline gives you. That would mean that your gas tank, quote unquote, would be a lot lighter, which means your car has less weight to pull around, which gives you much, much greater economy. Isn't that interesting? Let me show you another thing that I think is interesting. I'm going to try to write using this pen here. Let's look at that equation in the top for hydrogen. All right. So I'm going to write hydrogen plus oxygen and let's see what the product is going to be of that. Notice there's no carbon, so that means the only product you get is H2O. Sorry that my stylus is not very good. Let me see if I can complete these guys here. There you go. And of course, this is unbalanced here. You'd have to balance this equation here. We would need a 2 in here and a 2 in there. But notice my point here is that the only product you're getting out of this is water. Now you're familiar with carbon dioxide, right? What do we call that? What kind of gases does it belong to? It's one of the famous greenhouse gases, right? It is the one that is blamed for this phenomenon of global warming, because as it fills up the atmosphere, it creates the effect of a greenhouse. It concentrates the heat of the surface of the earth back, and so it causes global warming. So just so you know, I don't want to talk politics here, but let's understand a little bit of science. There is no scientific argument that global warming is not happening. It is happening, all right? The question, the debate is not whether it's happening or not. The debate is whether it's happening, A, because of increased amounts of CO2 in the atmosphere, and perhaps most importantly, is the excess CO2 the result of human activities. Okay, that's the debate that's being fought. And again, this is something I want you to get informed about. Don't believe everything you hear. Do your own research. And remember what I've always said, you guys are the generation that's probably going to shape the policies for the world that my grandkids are going to grow up in. So please inform yourself so that in the future, you will make good choices and contribute to a good world for my grandkids. All right? Or if not, I'll come back from the grave and haunt you. Several systems are in place for this. For example, I found this picture. The city of Cleveland in 2018 deployed these buses that run on hydrogen. It's very interesting. Just trying to, save the environment and decrease carbon dioxide emissions, which I thought was pretty cool. Now, just so you know, remember that when you look at that thing I just drew there, if you do the calculations here, and again, I'm sorry about my bad scribbling here. I have a really bad stylus here. But realize that a combustion reaction is a redox reaction. It's electrons being transferred. And you can see where the hydrogen is going to be reduced. It's going to be oxidized, and the oxygen is going to be reduced. So essentially, that transfer of electrons is what is responsible for that release of energy that we're talking about here. And the key in building a hydrogen fuel economy is not to burn it, because you simply burn the hydrogen in a combustion engine, you're going to have the same problems we have now. Yeah, you're not going to generate carbon dioxide, but you're going to generate, oxides of nitrogen and what other things that are in the atmosphere. So now what you do is you set up the redox reaction in two chambers. You separate the oxidation from the reduction halves, and you force the electrons to be transferred through a wire. Exactly. I'm talking about a battery. That's the way you do a hydrogen fuel economy. Okay, anyway, let's.